Okay, let's look at the neutralization reaction between hydrochloric acid and sodium hydroxide first. Now, what you see up top is going to be referred to as the molecular equation. This is the HCl aqueous plus NaOH aqueous yields NaCl aqueous plus H2O in a liquid phase. This is the equation that you normally see when we look at writing balanced chemical equations. And again, it's referred to as a molecular equation, even though the sodium hydroxide would be a formula unit and not a molecule, but that's what it is. And our first step would be to write the overall ionic equation. And what that means is we're going to write what the reactants and products are in aqueous solution in truth. And so because HCl is a strong acid, we're going to separate the hydrogen ion from the chloride ion. So we have H plus aqueous plus Cl minus aqueous. And again, as a note, you could write the H plus as H3O plus, and you would be perfectly fine doing that, because in reality, that's how it exists in water. But it is separated from the chloride. For simplicity's sake, just going to use H plus here, plus Cl minus, plus Na plus OH minus. So that's how our reactants exist in aqueous solution. When the neutralization reaction occurs, we'll have sodium ion, Na plus aqueous, plus Cl minus aqueous, plus H2O liquid. And what we want to do is we want to cross out the species that don't change phase or formula from the reactant to product side. Now, when we do that, I'm going to go ahead and just highlight the ones that are the same on both sides in red. But you could cross these out, and that's probably a better way to do it. But the Cl minus and the Na plus are both aqueous and separate on the reactant and product side, so we'd cross those out. And the net ionic equation will be the species that did not change formula, or excuse me, the net ionic equation will be the species that did change either formula or phase from one side or the other. So what we have is our H plus aqueous plus OH minus aqueous is going to form H2O liquid. And here is one of the reasons, for simplicity's sake, to just let the H plus be H plus rather than writing it as H3O plus, because you would just be able to form the water from the H plus and OH minus forming one water, whereas with H3O plus plus OH minus you would be forming 2H2O on the other side. So simplicity is the stronger hand here, and let's go with simplicity for our purposes. So again, the net ionic equation here is H plus OH minus, both of those aqueous, forming liquid water. And in their simplest forms, when you have a hydroxide containing base and an acid, it is a water forming reaction. So how'd you do? Let's look at our acetic acid plus potassium hydroxide reaction. The molecular equation is up top there. The overall ionic equation, because the acetic or ethanoic acid is a weak acid, we have to write it in its molecular form. The hydroxide, though, potassium hydroxide, will separate to K plus and OH minus. And on our product side, we'll have K plus the acetate ion, CH3COO minus, plus H2O. We'll cancel as appropriate, and the only thing we can cancel that's the same on both sides here would be the potassium ion. So our net ionic equation will be CH3COOH aqueous plus OH minus aqueous becomes CH3COO minus aqueous plus H2O. Now we have balanced in this net ionic equation both for atoms and for charge. If you'll notice that both the reactant side and the product side have a 1 negative charge. How'd you do? Here's our sulfuric acid, H2SO4, and magnesium hydroxide, MgOH in parentheses 2, forming magnesium sulfate, which is the salt, and water. And our overall ionic equation, remember with H2SO4, it's going to be written with just the one hydrogen ionized, so it would be H plus HSO4 minus. The magnesium hydroxide is a weak base, so we're going to write it as a formula unit, which would be considered its molecular form as a formula unit, and not separated as ions. So we have our MgOH in parentheses 2. When this reaction is done, we'll have magnesium ion, Mg2 plus aqueous, plus the sulfate ion, SO4 2 minus aqueous, and H2O. So even though H2SO4 ionizes just one hydrogen when you put it in water, the presence of the magnesium hydroxide during the neutralization process will cause the other hydrogen to ionize as well. But it will not ionize on its own in water. It has to have some help here. So our net ionic equation, we want to cancel what's the same on both sides. And one of the things that you'll notice is nothing cancels here. Nothing is the same on both sides. So our overall ionic equation is the same as our net ionic equation. How'd you do? Let's look at the reaction of hydroiodic acid with ammonia, NH3, and it forms ammonium iodide, which is an ionic compound. Now, here, water isn't formed because there's not hydroxide ion present in the base. This is a non-hydroxide ion containing base. So our overall ionic equation, hydroiodic acid is a strong acid, so we'll separate out the H plus aqueous and the I minus aqueous on the reactant side. NH3 is a weak base, so it's written in its molecular formula. On the other side, we'll form the ammonium ion, NH4 plus, and the iodide ion. We'll cancel as appropriate, and one of the things that will make sense here is the only thing that's the same on both sides in terms of formula and phase is the iodide ion. So that will cancel out, and we're left with a net ionic equation of H plus NH3 aqueous will form the ammonium ion, NH4 plus. And again, notice here that we've balanced not just for atoms, but for charge. If your charge is not balanced from one side to the other, something went wrong and you'll need to re-examine that. Our last one is the phosphoric acid, H3PO4, plus 3 sodium hydroxides forming sodium phosphate and water in the neutralization reaction. When we write the overall ionic equation, because H3PO4 is a weak acid, we write it in its molecular formula, not ionized, which is H3PO4, but we do separate our sodium ion from our hydroxide ion, which would be appropriate because it's a strong base. And so we have our 3Na plus 3OH minus. On the other side, the product side, we have 3Na plus PO4 3 minus plus 3H2O. Now, we cancel as appropriate here. We cancel what's the same in terms of formula and phase on both sides. And in this case, it is just the sodium. So we cancel the 3 sodiums on the reactant and product sides. And our net ionic equation then is H3PO4 plus 3OH minus will yield PO4 3 negative aqueous, which is the phosphate ion, and 3 waters. So how'd you do? We've come to the end of part 2 of the video podcast series having to do with acid-base fundamentals. And I want to leave you with a quote from a former president, Richard M. Nixon. Always remember that others may hate you, but those who hate you don't win unless you hate them, and then you destroy yourself. I wish you well. There's more to come, so please engage.